In the previous lecture, you got a good initial impression about asymptotic series and have considered some examples of how to calculate asymptotic representations for some particular integrals. In this lecture, we will study a bit more general way to calculate asymptotic expansions of integrals, and this way which we will discuss is called Laplace method. So basically, just a brief reminder, in the previous lecture you were dealing with the integral of the following form. And in your particular example, the function f of x had a form of 1 over 1 plus x. And as you remember, a way to derive asymptotic expansion of this integral was just to expand this fraction in Taylor series near the origin. Basically, this procedure assumes that dominant contribution to this integral comes from small x. Of course, this is not the most general situation with definite integrals, and in this lecture we will discuss a bit more general setup. And we will start with the integral of so-called Laplace form. This integral has the following structure. So first of all, it usually has form of product of two functions. One of them is exponential, and in this exponential there is a large parameter, lambda, which will be assumed to be much larger than 1. And crucial point in this Laplace form is that all other terms of this integral, they do not depend on lambda. In particular, the integration range a and b are assumed to be some constants, and function g of x is assumed to be a smooth function on the whole integral range of integration. And in addition, it is assumed to be of the order of 1, in the sense that it doesn't have a large parameter lambda inside. So this is the one of the most general forms of asymptotic integrals. And let us discuss some particular example, how it can look like. We will turn to this example a bit later, but we will start with identifying that this integral has Laplace form. So for example, compare these two expressions, general I of lambda and this particular one. So obviously, this function in the exponential, which is multiplied by a large parameter, is f of x. And in this particular example, g of x is 1. And in addition, the integration limits are fixed, meaning they do not depend on lambda, and the integration goes from 0 to infinity. We will come back to this particular example a bit later, and now let us discuss some generalities of the Laplace integral. So let us turn back to the most general form of I of lambda, and suppose now f of x has maximum inside the integration range at some particular point x0. Typical shape of this function of exponent of lambda f of x is shown on the right hand side of the slide. And in principle, it can be a rather complicated function, but as long as lambda is large, of course, it's almost immediately obvious that this integral, the whole integral, is dominated by a small vicinity of the point x0. And in this case, we of course are not interested in full details of the function f of x, but instead we are only interested in details of its structure in the vicinity of the extrema. And in this case, we can substitute the full function f of x by its Taylor series. And in this expression, which you see on the left-hand side, notice that there is no term proportional to x minus x0. This is, of course, immediate consequences of extremality of the function f of x at point x0. As a result of such approximation, we already see that our Laplace integral simplifies, mostly due to substitution of the full form of f of x by its Taylor expansion. And on the right-hand side, you see how the plot is modified. And in line with what we just discussed, we see that the change in the vicinity of the maxima is negligible, and at the same time, the changes at the tails of this function, of course, can be much more substantial, but they are of no importance for the full integral, because this integral is dominated by extrema of the integrand. Some more approximations are on the way, and in particular, first approximation is to substitute full function g of x by its value in the vicinity of the point of extrema, g of x0. And final approximation is not to care about details of the original integration domain A and B, but instead to integrate from minus infinity to plus infinity. And this approximation is again justified by the fact that parameter lambda is large, and of course the function in the exponent is large only as long as x belongs to some tiny region between x naught minus 1 over square root lambda and x naught plus 1 over square root lambda. So basically the integration range effectively is determined by width of the function f of x in the exponential. And we can forget about true integration range. And finally, a closer inspection of this integral shows that it actually, in this form, it can be calculated exactly. In order to calculate it, we recall well-known formula for Gaussian integrals, which we will use many times from now. And I will show you in next lecture a couple of times this formula again. But for the moment, of course, using it, we immediately come to a final result. And this result is of the following form. Notice that this final expression is applicable for wide class of function f of x and g of x. And for the moment, we do not assume specific form of these functions, but instead write some general result, which we will use in the next slide. So now we are going to apply this our general understanding of Laplace method and properties of Laplace integral to some particular example. In fact, this is almost the best known asymptotic formula, so-called Stirling formula, which we are now going to derive. And in this formula, we are going to discuss the properties of the factorial function. And from the form of this factorial function, it's immediately obvious that this function grows quite fast. And in fact, our question in this section will be how fast is this growth actually is. So in order to understand the properties of this factorial function at large n, we will use integral representation of this function. In fact, this representation was derived for you in one of the previous lectures. And in order to make this more obvious, I will rewrite this integral here in a bit different way. So after very simple transformation, you see that this integral is actually nothing but integral of exponent minus t to power n dt from 0 to infinity. And as you remember, this is nothing but factorial function, which can this fact can be shown by differentiation over parameter. And this is the formula which we use as the basic one in this lecture. But before proceeding with this, let us see if we can get some intuitive understanding of these properties of factorial function at large n. And for example, we can ask ourselves how quickly the log of the factorial grows with n. And the simplest way to do this is to recall that this is nothing but log of the following product. And by well-known properties of logarithm, we immediately realize that this is sum of logarithms of integer numbers. And here we go with our first approximation and substitute this sum over integer numbers by an integral. And this is a standard approximation, which we now employ in the following form. And it is interesting that this integral, which is now an approximation for the log of factorial, can be calculated exactly. By integration of parts, you can show that this integral is nothing but x log x minus x. And immediately you can figure out that after exponentiating this approximate equality, that factorial of n grows roughly as n over e to the power of n. This is already a very reasonable approximation, but our question will be how to make it even better, and probably how to make it as accurate as we would like by deriving asymptotic series for this function. So this is our motivation. And as a first step, we recall our general form of the Laplace integral. And from the first sight, by comparing these two expressions, we may think that they are not so similar. And in fact, the main difference is that in the general form of the Laplace integral, the large parameter lambda multiplies expression in the exponent homogeneously. But from the other side, in our expression for factorial function, n doesn't enter exponential term homogeneously. But of course, this can be rather straightforwardly fixed. And this fix just reduces to change of the integration variable. So instead of integrating over t, we introduce new variable s, which is just linearly connected to original variable t. And immediately, by substituting this change of variables in our original integral, we come to our final expression, which we'll be dealing with in what follows. And in fact, you can notice that this expression is actually already of standard Laplacian form, with function f of s equal to log s minus s. Now, in order to apply the general scheme which we discussed in the previous lecture to this particular integral, we need to understand what are the properties of the function f of x. And in fact, it's quite straightforward to figure this out. Why? Because at large s, this function is dominated by second term, minus s. And at small s, this function is dominated by log s. And as it is obvious from this plot, this function has a maximum somewhere between 0 and infinity. And in fact, the width of this maximum in the full function exponent of n f of s becomes smaller and smaller with growth of n. This is exactly the property which we need in order to calculate the asymptotic of this integral. So, as we just discussed, the maximum is obtained inside the integration range, and the particular point x0 at which the maximum is obtained can be found by just looking for the 0 of the derivative. So in this particular case, this function becomes... Так, немножко там перескочило, но случайно совершенно. In this particular case, this equation becomes... And as a result, the point of extrema is s equal 1. And in this, all what we need to know from this function is how exactly it behaves in the vicinity of the maxima. And this can be found out by calculating the second derivative. So as a result, we are dealing with the following approximation for this more complicated function in terms of quadratic function of x. Finally, as you remember from the previous lecture, our next step is to substitute this approximation into the full integral. So instead of f of x, s here, we substitute its quadratic approximation. And as a result, we come to Gaussian integral. Let me remind you how to evaluate this integral. For this, we use the standard form of the Gaussian integral, and you can see immediately that what is the structure of this expression. So first of all, there is a term which does not depend on s. Of course, it just factorizes from the full integral. And there is a term which, by shift of the integration variable, turns to its standard form. And as a result, we come to our final answer. And we find out that a factorial grows as, let us compare it with our previous naive estimation from the integral. And as you remember, we, by our naive qualitative reasoning, we found out that n factorial should be of the order of n over e to the power of n. And as a result of this more accurate treatment in terms of Laplace approximation, we found out that there is at least important factor, which is square root of n.